Picture this, you're staring up at the night sky, lost in the vast ocean of stars. Now imagine every single one of those stars is moving away from you faster today than it was yesterday. And tomorrow, it'll race away even quicker. This isn't science fiction, it's our universe right now, expanding at breakneck speed with no cosmic breaks in sight. The strangest part, the force behind this runaway expansion makes up nearly 70% of everything in existence, yet we can't see it, touch it, or even fully explain it. Scientists call it dark energy, and it's rewriting everything we thought we knew about reality. Stick around, because by the end of this journey, you'll understand why this invisible force might hold the ultimate secret to the fate of everything, from distant galaxies to the device you're watching this on right now. Now, let's rewind the cosmic clock to a groundbreaking moment in science. In 1998, two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, made a discovery so shocking it flipped our understanding of the universe upside down. They were studying distant supernova exploding stars so bright they can outshine entire galaxies, using them as cosmic mile markers to measure how fast the universe was expanding. Here's where things got weird. Instead of finding that the expansion was slowing down as everyone expected due to gravity's pull, they saw the opposite. The universe wasn't just expanding, it was speeding up as if some invisible force was giving it an extra push. This was like tossing a ball in the air and watching it shoot faster into the sky instead of falling back down. The discovery was so monumental it earned them the Nobel Prize in Physics in 2011, and it forced scientists to confront a humbling truth. Everything we thought we knew about the universe's fate was wrong. Dark energy wasn't just a curiosity, it was the dominant player in the cosmic game, rewriting the rules as we watched. Now, let's untangle two of the biggest cosmic puzzles that often get mixed up: dark energy and dark matter. Picture them as the universe's ultimate tug-of-war team, but with completely opposite game plans. Dark matter is like the invisible glue holding galaxies together. It's the reason stars on the edges of galaxies don't just fly off into space. We can't see it, but its gravity keeps everything from falling apart. Think of it as the cosmic scaffolding that shapes the universe's structure. On the other side, dark energy is the mysterious force doing the exact opposite. Instead of pulling things together, it's pushing the universe apart, accelerating its expansion like an unstoppable cosmic wind. While dark matter works behind the scenes to bind galaxies into clusters, dark energy is stretching the very fabric of space itself, making sure those clusters drift farther and farther apart over time. Here's the wild part: even though they're polar opposites, together they make up about 95% of the universe's total content. The stuff we actually see, planets, stars, and galaxies, is just a tiny fraction of what's out there. So next time you look up at the night sky, remember, most of what's shaping the cosmos is completely invisible, working in ways we're still struggling to understand. And speaking of understanding, let's take a closer look at one of the earliest ideas that might explain dark energy: Einstein's so-called biggest blunder. Now, here's a twist in the story. Einstein himself might have accidentally predicted dark energy long before anyone even knew it existed. Back in the early 20th century, he introduced something called the cosmological constant, a mathematical term he added to his equations of general relativity. At the time, Einstein believed the universe was static, neither expanding nor contracting, so he tweaked his theory to keep it that way. But when astronomers later discovered the universe was actually expanding, Einstein called this adjustment his biggest blunder and dismissed the idea entirely. Fast forward to the late 1990s, when scientists found that the expansion wasn't just happening, it was speeding up. Suddenly, the cosmological constant didn't seem like a mistake anymore. In fact, it turned out to be a brilliant, if unintentional, prediction of dark energy. Today, physicists see the cosmological constant as the simplest explanation for dark energy, a constant, unchanging force woven into the fabric of space itself. It's like an invisible energy field that never weakens, steadily pushing the universe apart. But here's the catch: while it fits the data well, it also raises new questions. Why does this energy have the exact strength needed to match what we observe? And if it's truly constant, what does that mean for the universe's ultimate fate? Einstein's so-called blunder might hold the key to one of the biggest mysteries in physics. And as we dig deeper, we'll see how modern science is still wrestling with its implications. Now, let's take a step into the bizarre world of quantum physics, where even empty space isn't as empty as it seems. At the tiniest scales, what we think of as a vacuum is actually a seething sea of activity, virtual particles popping in and out of existence in a flash. These fleeting particles borrow energy from the universe, appearing and vanishing so quickly that we can't directly detect them. But here's the wild part: this quantum foam isn't just a curiosity. It might hold the secret to dark energy's repulsive force. According to quantum theory, this vacuum energy should have a real, measurable effect on space itself. In fact, if you add up all these tiny fluctuations, they should produce an enormous amount of energy, enough to warp the fabric of the cosmos. The problem: when physicists try to calculate how much energy this quantum vacuum should have, the numbers come out absurdly large, way beyond what we observe in dark energy. This mismatch is one of the biggest unsolved puzzles in physics, yet the idea remains compelling. If this vacuum energy exists even at a weaker scale, it could act like a kind of anti-gravity, pushing space apart instead of pulling it together. Picture it like an invisible spring embedded in the universe, constantly stretching it outward. That's why some scientists think dark energy might be tied to these quantum fluctuations, a cosmic pressure born from the restless energy of empty space. But the mystery deepens. If quantum vacuum energy is real, why is its strength so finely tuned to match the universe's expansion? And why doesn't it overwhelm everything else? These questions take us to the edge of our understanding, where quantum physics and cosmology collide. As we peel back the layers, we'll see how this quantum enigma might reshape our view of dark energy and the universe itself. Now, let's fast forward billions of years into the future and ask what happens if dark energy keeps pushing the universe apart. One chilling possibility is the Big Freeze. Imagine a cosmos where dark energy's relentless push accelerates so much that distant galaxies vanish from view, one by one. Over time, even the closest galaxies would drift beyond our cosmic horizon, their light stretched too far to ever reach us. The universe would become a vast, empty expanse, cold, dark, and eerily still. Stars would burn out, black holes would evaporate, and space itself would approach absolute zero. It's a lonely ending where the universe fades into silence, but the Big Freeze isn't the only fate on the table. Some theories suggest something far more violent: the Big Rip. Here, dark energy doesn't just push galaxies apart. It grows stronger over time, eventually overpowering gravity's hold on everything. First, galaxy clusters would tear apart, then individual galaxies, then stars, planets, and even atoms themselves. Space itself would rip at the seams, shredding the fabric of reality in a catastrophic finale. The difference between these two scenarios hinges on dark energy's behavior. If it stays constant, the Big Freeze wins, but if it intensifies, the Big Rip takes the stage. Right now, observations suggest dark energy is steady, but we can't rule out a future where it turns phantom. Either way, the universe's fate rests on this invisible force, and unraveling its secrets could tell us whether our cosmos ends with a whisper or a scream. Next, we'll look at the tools scientists use to measure dark energy's grip on the universe, and how they're racing to uncover which of these futures awaits us. To uncover the secrets of dark energy, scientists rely on a cosmic toolkit designed to measure its invisible influence. One of the most powerful tools in this arsenal is Type 1, a supernova. These exploding stars shine with such consistent brightness that they act like cosmic lighthouses, allowing astronomers to gauge distances across the universe. By observing how dim these supernovae appear, researchers can calculate how fast the universe is expanding and how dark energy is driving that acceleration. But supernovae aren't the only clue. Another method involves baryon acoustic oscillations, subtle ripples frozen in the fabric of space from the universe's earliest moments. These ripples act like a giant ruler, imprinting a predictable scale on the distribution of galaxies. By mapping where galaxies cluster, scientists can measure how dark energy has stretched the universe over billions of years. Then there's weak gravitational lensing, a phenomenon where the gravity of massive objects bends light from distant galaxies, distorting their shapes. By studying these distortions, researchers can trace the invisible scaffolding of dark matter and see how dark energy reshapes it over time. What's remarkable is how these methods cross-check each other. Supernova, baryon oscillations, and lensing all paint the same picture. Dark energy is real, it's relentless, and it's shaping the fate of everything. Up next, we'll dive into the equation that defines dark energy's mysterious behavior and why even a tiny tweak to it could rewrite our cosmic future. Now let's crack open the equation that holds the key to dark energy's secrets. At the heart of this cosmic puzzle is a single parameter scientists call W, a deceptively simple number that defines how dark energy behaves. Think of it as the universe's pressure dial. This ratio compares dark energy's pressure to its density, and its value tells us whether the expansion of the cosmos will slow down, speed up, or even tear reality apart. When W equals -1, it matches Einstein's cosmological constant, a steady, unchanging force woven into space itself. This would mean dark energy's push remains constant over time, leading to a universe that expands forever, growing colder and emptier. But what if W isn't exactly -1? Even a tiny deviation could rewrite everything. A value slightly higher might suggest dark energy weakens over time, while a lower one could mean it grows stronger, potentially leading to a catastrophic big rip where galaxies, stars, and even atoms are torn apart. The hunt for W's true value is one of the biggest challenges in cosmology. Current observations peg it close to -1, but the margins of error leave room for mind-bending possibilities. If future telescopes detect a deviation, it could mean dark energy isn't a constant at all, but something dynamic, like a mysterious field evolving across cosmic history. That would upend our understanding of physics, forcing us to rethink gravity, quantum theory, and the very fabric of reality. Up next, we'll explore the bold thinkers who argue that dark energy might not even exist, and why some believe Einstein's theory of gravity itself needs a rewrite. But what if the answer isn't out there in the form of dark energy at all? Here's a twist. Some scientists believe the real mystery lies closer to home, in the laws of gravity themselves. Instead of invoking an invisible force pushing the universe apart, they argue that Einstein's theory of relativity might need an update. Take modified Newtonian dynamics, or MUND for short. This idea suggests that gravity behaves differently on cosmic scales than it does in our solar system. In places where gravity seems too weak to hold galaxies together, like their outer edges, MUND proposes a tweak to the math, eliminating the need for dark matter. But could a similar adjustment explain cosmic acceleration without dark energy? Supporters point to oddities in galaxy rotations and cluster motions as clues that gravity might not play by Einstein's rules everywhere. Then there's F of R gravity, a more complex alternative where gravity's strength changes depending on the curvature of spacetime. Picture spacetime as a stretchy fabric. In this model, it might resist bending differently in empty voids versus crowded galaxy clusters. If true, this could mimic dark energy's effects, making the universe appear to accelerate when really, our math was just incomplete. Critics fire back that these theories struggle to explain all the evidence. For instance, they don't neatly account for the patterns seen in the cosmic microwave background or the precise distribution of galaxies. Yet the debate rages on because if either mund or F of our gravity is right, it would mean dark energy is a cosmic mirage, and Einstein's greatest work isn't the final word after all. Next up, we'll dive into another fascinating possibility. That dark energy isn't a constant force, but a shifting, evolving entity known as quintessence. Could this be the key to unlocking the universe's expansion? Now let's explore a different angle. What if dark energy isn't a fixed feature of the cosmos, but something that changes over time? Enter quintessence, a theory that paints dark energy as a dynamic force, almost like a cosmic weather system shifting across the ages. Unlike the cosmological constant, which stays stubbornly the same everywhere, quintessence suggests dark energy could have been stronger or weaker in the past and might even evolve in the future. Imagine the universe as a stretchy canvas, with quintessence acting like an invisible hand that adjusts its push depending on when and where you look. Early in cosmic history, this hand might have pressed lightly, allowing galaxies to form. But today, it could be pushing harder, speeding up expansion. Some models even suggest quintessence might one day fade away or flip entirely, pulling the universe back together in a dramatic reversal. How do we test this idea against the steady hum of the cosmological constant? Future telescopes like Euclid and the Roman Space Telescope will map the universe's expansion with razor-sharp precision, hunting for tiny wrinkles in the data that reveal whether dark energy's strength has changed over billions of years. Another clue lies in how quintessence interacts with matter. If it tugs slightly on galaxies or alters the cosmic web's structure in unique ways, those fingerprints could set it apart from Einstein's static vacuum energy. The stakes are high. If quintessence is real, it wouldn't just rewrite dark energy's story, it could hint at entirely new physics, perhaps even a connection to the mysterious fields that drove inflation after the Big Bang. Up next, we'll see how dark energy's fingerprints aren't just written in the future of the cosmos, but etched deep into the architecture of the universe itself, the cosmic web. Now let's zoom out and see dark energy's grand masterpiece, the cosmic web. Picture the universe not as a random scatter of galaxies, but as an intricate network of threads, vast walls, and enormous voids, all woven together over billions of years. This sprawling structure didn't form by accident. Dark energy has been the invisible architect, subtly shaping where galaxies gather and where they don't. Here's how it works. In the early universe, gravity was the dominant force, pulling matter into dense knots that became galaxy clusters. But as dark energy took over, it began pushing space itself apart, making it harder for new clusters to form. Think of it like trying to build a sandcastle. As the tide comes in, the waves keep pulling the sand away. Dark energy does something similar, stretching the cosmic canvas so fast that matter can't clump together as easily. Simulations show this drama playing out on a colossal scale. Without dark energy, the universe would be packed with far more galaxy clusters, a crowded cosmic metropolis. Instead, we see a sparser web with vast empty voids separating thin filaments of galaxies. These voids aren't just empty space, they're evidence of dark energy's relentless push, clearing out regions where gravity once ruled. But the cosmic web isn't just a fossil of the past, it's still evolving today. By studying how galaxies are distributed, especially in the most distant, ancient corners of the universe, scientists can measure dark energy's fingerprints in real time. Up next, we'll tackle one of cosmology's biggest headaches, the Hubble tension, where conflicting measurements of the universe's expansion rate might just reveal dark energy's secrets are even stranger than we thought. Now let's untangle one of the biggest puzzles in modern cosmology, the Hubble tension. Imagine measuring the speed of a car with two different tools, only to get wildly different results. That's essentially what's happening with the universe's expansion rate. On one hand, we have precise measurements from the Planck satellite, which studied the cosmic microwave background, the afterglow of the Big Bang. These observations suggest the universe is expanding at a certain speed, known as the Hubble constant. But here's where things get weird. When astronomers measure the expansion rate using nearby objects like supernova or Cepheid stars, tools we've trusted for decades, they get a noticeably faster result. This discrepancy isn't just a small rounding error. It's a gap that's persisted despite years of rechecking data and refining methods. So what's going on? Some scientists think dark energy might hold the key. If dark energy isn't constant but instead grows stronger over time, it could explain why local measurements show a faster expansion than those based on the early universe. Picture a car that starts slow but gradually hits the gas pedal harder. Dark energy could be doing the same to cosmic expansion. Others argue the tension might reveal flaws in our understanding of gravity or hidden properties of neutrinos. But one thing's clear, this isn't just academic bickering. If dark energy is changing, it would rewrite our cosmic playbook, altering predictions about the universe's fate. Up next, we'll look at the cutting-edge telescopes poised to solve this mystery, from Euclid to the Roman Space Telescope, and how they might finally crack dark energy's code. Turning our gaze to the future, a new generation of cosmic explorers is about to take center stage. These cutting-edge observatories are designed to tackle dark energy's biggest mysteries head-on. First up is the European Space Agency's Euclid mission, set to launch with one clear goal: map the shapes and positions of over 1 billion galaxies across 10 billion light-years of space. By measuring how these galaxies are subtly distorted by dark energy's push, Euclid could reveal whether this force has changed over cosmic history. Then there's NASA's and Nancy Grace Roman Space Telescope, often called Hubble's powerful successor. With a field of view 100 times wider than Hubble's, Roman will scan the sky at breakneck speed, capturing supernova and galaxy clusters in unprecedented detail. Its observations could settle the Hubble tension once and for all by delivering the most precise measurement yet of the universe's expansion rate. Not to be outdone, the ground-based Large Synoptic Survey Telescope, or LSST, will take this hunt to the next level. Every few nights, its massive mirror will photograph the entire southern sky, creating a time-lapse movie of the cosmos. By tracking how galaxies move and cluster over time, LSST might catch dark energy in the act, showing us whether it's a constant force or something far more dynamic. Together, these missions represent humanity's most ambitious attempt to decode dark energy. They'll peer deeper into space and further back in time than ever before, turning vague theories into concrete answers. What they find could either confirm our current models or force us to rewrite the rules of cosmology entirely. But the story doesn't end there. Beyond these telescopes lies an even bigger question. Why did dark energy stay hidden for so long in the universe's early days? That's a puzzle we'll explore next as we dig into dark energy's elusive behavior during the cosmos' infancy. Now, let's rewind the cosmic clock to a time when dark energy was barely a whisper in the universe's story. Here's the puzzle. If dark energy makes up nearly 70% of the cosmos today, why was it practically invisible in the early universe? This is what scientists call the dark energy swindle, and it's one of the most baffling fine-tuning problems in physics. Picture the universe just moments after the Big Bang, a seething hot soup of particles and radiation. Back then, matter and energy were packed so tightly that gravity ruled supreme, pulling everything together. Dark energy, weak as it was, couldn't compete, but as the universe expanded and matter spread out, gravity's grip loosened. That's when dark energy, once a background player, stepped into the spotlight. This raises a haunting question: why did dark energy's strength seem perfectly timed to take over only after galaxies and stars had formed? If it had dominated earlier, the universe would have expanded too rapidly for structures to ever clump together. No galaxies, no stars, no us. It's as if the cosmos knew the exact moment to flip a switch, and physicists still can't explain how or why. Some theorists see eerie parallels between dark energy and inflation, that brief period of hyper-expansion right after the Big Bang. Both involve mysterious repulsive forces that shape the universe's fate. Could dark energy be inflation's distant cousin, a weaker echo of that primordial push? Or is its late rise a clue that we're missing something fundamental about how gravity works across cosmic time? The deeper we dig, the stranger it gets. Dark energy's elusive behavior in the early universe isn't just a curiosity, it's a glaring gap in our understanding of reality itself. And as we'll soon see, things get even weirder when we consider the most extreme possibilities dark energy might unleash. Now, let's take a step into the realm of the truly bizarre phantom energy. Imagine dark energy not just as a steady force, but one that grows stronger over time. This isn't science fiction. Some models suggest dark energy's density could increase, with its equation of state dropping below -1. If that happens, the universe's fate takes a terrifying turn. Picture this: phantom energy doesn't just push galaxies apart. It accelerates the expansion so violently that eventually, even the fabric of space-time can't hold together. First, galaxy clusters are ripped apart. Then, individual galaxies, stars are torn from their orbits, planets are shredded, and in the final moments, atoms themselves are pulled apart. This is the Big Rip, a cosmic doomsday where everything, down to the smallest particles, is obliterated by dark energy's unstoppable grip. What makes phantom energy so unsettling is how little we know. Could this really happen? Right now, observations suggest dark energy behaves like a cosmological constant, with its density staying steady. But the universe has surprised us before. If future telescopes detect even a slight deviation, if that mysterious W parameter creeps below -1, the Big Rip moves from theory to genuine possibility. And here's the chilling part: if phantom energy is real, the countdown isn't in billions of years. Depending on how fast it grows, the end could come in as little as a few tens of billions of years. For context, that's before our sun even dies. The universe might not get the slow, cold fade out we once imagined. Instead, it could meet a violent, dramatic end. This raises even deeper questions. Is phantom energy a flaw in our models or a real cosmic threat? Could it be tied to undiscovered physics like quantum gravity or extra dimensions? For now, it remains one of the most extreme and unsettling possibilities dark energy has to offer. And as we'll see next, the mysteries don't stop there. Now, let's shift our gaze to an even more mind-bending idea. What if dark energy isn't just a mysterious force in our universe, but a cosmic accident? This is where string theory enters the picture. Imagine a universe not with 3 dimensions of space and 1 of time, but with 10 or even 11 dimensions curled up so small we can't detect them. String theory suggests that every possible configuration of these extra dimensions creates a unique vacuum state, a different version of reality with its own laws of physics. In this vast landscape of possibilities, dark energy might not be special at all. Our universe could simply be one where the value of dark energy happens to allow galaxies, stars, and life to exist. Other universes might have too much dark energy, ripping themselves apart before anything can form, or too little, collapsing back into a cosmic crunch. It's a humbling thought our entire existence might hinge on a random draw from an infinite multiverse. But here's where it gets even stranger. String theory doesn't just predict multiple universes, it suggests they're constantly popping into existence, each with its own version of dark energy. Some physicists argue this could explain why our dark energy is so small yet not zero. If most universes are uninhabitable, we'd naturally find ourselves in one of the rare, life-friendly ones. It's called the anthropic principle, and while it's controversial, it forces us to ask, is dark energy a fundamental law or just a lucky roll of the dice? Of course, string theory remains untested, and the multiverse is still speculative. But if future experiments find evidence of extra dimensions or other universes, it could rewrite our understanding of dark energy entirely. For now, it's a tantalizing possibility, one that blurs the line between physics and philosophy. And as we'll see next, this isn't the only way dark energy challenges our place in the cosmos. Now, let's take a step back and consider something even more profound. Why does dark energy have the exact value it does? Is it just a cosmic coincidence, or is there something deeper at play? This brings us to the anthropic principle, a fascinating idea that suggests dark energy's value might not be random at all. Instead, it could be precisely tuned to allow life like ours to exist. Think about it this way. If dark energy were even slightly stronger, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. Everything would be ripped apart before it had a chance to come together. On the other hand, if dark energy were weaker, gravity would have pulled the universe back into a fiery collapse long before life could emerge. It's as if the universe is walking a tightrope, balancing between two extremes, and somehow we're here to witness it. But here's where the debate gets heated. Some scientists argue this fine-tuning is evidence of a deeper law or principle we haven't discovered yet. Others say it's just luck, a random outcome in a multiverse where countless universes exist, each with different dark energy values. In most of those universes, conditions would be too hostile for life, but in a rare few like ours, everything lines up perfectly. This raises a mind-bending question. Are we here because the universe was designed for life, or are we simply the winners of a cosmic lottery? The anthropic principle doesn't answer that, but it forces us to confront the eerie precision of dark energy's influence. Whether it's a fundamental law or a statistical fluke, one thing is clear: dark energy doesn't just shape the universe. It might also be the reason we're here to study it. And as we'll see next, this isn't the only way dark energy bends our understanding of reality. Its influence stretches even further, challenging the very fabric of time itself. But what if dark energy isn't just shaping space? What if it's also warping time itself? This is where things get even stranger. Imagine a universe where dark energy isn't constant but changes over time, subtly tweaking the cosmic clock. Some scientists think this could explain puzzling quirks in the light from distant quasars, those brilliant beacons powered by supermassive black holes. Their light sometimes arrives with unexpected delays or distortions, almost as if something, perhaps dark energy, is stretching the fabric of time along its journey. Then there's the early dark energy hypothesis, a bold idea suggesting dark energy wasn't always the quiet background force we see today. In the universe's infancy, it might have pulsed with activity, accelerating expansion briefly before fading into obscurity. If true, this could solve a cosmic riddle: why dark energy's influence seems so finely tuned now. Maybe it wasn't tuned at all. Maybe it evolved, leaving behind clues in the ancient light of the cosmos. Of course, not everyone's convinced. Skeptics argue these anomalies could just be measurement errors or gaps in our understanding of quasars themselves. But if time-varying dark energy is real, it would rewrite the rules of cosmology. Suddenly, dark energy isn't just a mysterious push, it's a dynamic player in the universe's story, one that might have left fingerprints in the past and could still be shaping our future. And speaking of the future, our next frontier lies in the lab, where scientists are attempting the seemingly impossible: detecting dark energies whisper right here on Earth. Now, let's step away from the cosmos for a moment and into the lab, where scientists are tackling dark energy on a much smaller scale. Believe it or not, researchers are trying to detect this elusive force right here on Earth, using tools so precise they can measure the faintest whispers of the universe. One approach involves the Casimir effect, a strange phenomenon where two tiny metal plates placed incredibly close together in a vacuum experience an invisible push. This happens because the quantum fluctuations in empty space, those same virtual particles we mentioned earlier, create a subtle force between the plates. Some scientists think this could be a hint of dark energy's influence, a tiny echo of the repulsive force driving cosmic expansion. Then there's atom interferometry, a mind-bending technique where scientists use lasers to split and recombine atoms, measuring how their paths change. The idea is that dark energy might leave an imprint on these ultra-sensitive experiments, warping space ever so slightly in ways we could detect. But here's the catch: these lab tests face enormous challenges. Dark energy's effects are unimaginably weak on small scales, drowned out by everything from vibrations in the lab to the gravitational pull of a passing truck. It's like trying to hear a pin drop in a hurricane. That's why these experiments require insane levels of precision, often operating in underground facilities to shield them from even the slightest interference. And yet, the payoff could be huge. If we could detect dark energy in a lab, it wouldn't just confirm its existence, it might reveal whether it's truly constant or changing over time, unlocking secrets about the universe's fate. So while these experiments might seem like long shots, they're pushing the boundaries of what's possible, bringing us one step closer to solving the mystery of dark energy. Up next, we'll explore how this enigmatic force isn't just a scientific curiosity. It's reshaping our very understanding of reality, from philosophy to pop culture. But dark energy isn't just a puzzle for scientists, it's seeped into the very fabric of our culture, reshaping how we see our place in the cosmos. Think about films like Interstellar, where the Tesseract, a mind-bending higher dimensional space, mirrors the strangeness of dark energy's repulsive force. Sci-fi often borrows these cosmic mysteries to explore big questions. Are we alone? Is the universe indifferent to us? Dark energy, with its invisible grip on reality, fuels those stories, turning them into metaphors for human curiosity and insignificance. Philosophers, too, grapple with its implications. If dark energy keeps pushing galaxies apart, leaving us isolated in an ever-expanding void, what does that mean for humanity's future? Some argue it underscores our fragility, a reminder that the universe doesn't revolve around us. Others see it as a call to explore, to push boundaries before the cosmos drifts out of reach. Even in art and music, dark energy's eerie influence creeps in. Album covers, paintings, and installations evoke its vast, unknowable nature, playing with themes of emptiness and expansion. It's become a symbol of the ultimate unknown, a blank canvas for our fears and imaginations. So are we just bystanders in this anti-gravitational drama? Maybe, but dark energy also reminds us that the universe is full of wonders we've yet to understand, and that's what keeps us searching, creating, and looking up at the stars. Next, we'll hear from the skeptics, those who question whether dark energy exists at all, and what that debate means for science. Now, let's turn the spotlight on a different perspective, one that challenges the very foundation of what we think we know about dark energy. Not everyone in the scientific community is convinced it exists at all. Some researchers argue that what we're calling dark energy might actually be a misinterpretation of the data, a cosmic illusion caused by gaps in our understanding. Take, for example, the idea of systematic errors. These skeptics point out that tiny inaccuracies in measuring supernova or galactic distances could snowball into the illusion of an accelerating universe. Imagine trying to measure the speed of a car with a slightly broken speedometer. You might think it's accelerating when it's really just your tool giving you faulty readings. Could our telescopes and algorithms be doing the same thing on a cosmic scale? Then there's the inhomogeneous universe theory. Our models often assume the cosmos is smooth and evenly distributed, like a perfectly mixed cake batter. But what if it's lumpy, with dense clusters of matter and vast empty voids? these irregularities could warp our observations, making it seem like space is expanding faster than it really is. It's like looking at a funhouse mirror. The reflection isn't reality, just a distortion. And let's not forget modified gravity theories like MUND, which tweak Einstein's equations to explain galactic motions without invoking dark energy. If gravity behaves differently on cosmic scales than we thought, maybe we don't need an invisible force to explain the universe's expansion. It's like realizing you've been using the wrong recipe all along. The mystery ingredient might not exist. Of course, these alternatives have their own hurdles, but that's the beauty of science. It thrives on doubt, on testing every assumption until the strongest idea survives. Whether dark energy is real or just a placeholder for something even stranger, the debate itself pushes us closer to the truth. Up next, we'll explore how dark energy might interact with one of the universe's most enigmatic phenomena, black holes. Now, let's venture into one of the most intriguing intersections in modern physics, where dark energy meets the enigmatic realm of black holes. If dark energy is indeed stretching the fabric of space itself, how does that affect these cosmic vacuum cleaners? First, consider black hole evaporation. Thanks to Stephen Hawking's groundbreaking work, we know black holes aren't entirely black. They slowly leak radiation and lose mass over time. But here's the twist. Dark energy's repulsive force could alter this process. Imagine a black hole sitting in an expanding universe where space itself is being pushed apart. Some theories suggest this expansion might dilute the Hawking radiation, making black holes evaporate even slower. It's like trying to boil water in a pot that's constantly getting bigger. The heat dissipates more weakly, slowing the process down. Then there's the singularity, the infinitely dense core of a black hole where our understanding of physics breaks down. Could dark energy influence this mysterious point? In some models, dark energy's push might counteract the crushing gravity near the singularity, subtly changing its behavior. Think of it as a cosmic tug of war, gravity pulling matter inward while dark energy tries to stretch space outward. The balance between these forces could redefine what happens in the black hole's deepest depths. But here's where it gets even wilder. If dark energy's strength changes over time, as some dynamic theories suggest, it might unpredictably affect black hole evolution. A growing dark energy density could one day dominate even these gravitational monsters, potentially altering how they merge, spin, or vanish. It's a reminder that in an accelerating universe, even the most extreme objects aren't immune to the dark energy's whisper. Up next, we'll take a step back and ask an even bigger question. Could dark energy be just one random possibility in a vast multiverse of cosmic recipes? The answer might reshape everything we think we know about reality. Now, let's stretch our imaginations even further into the mind-bending realm of the multiverse. If dark energy is the mysterious force driving our universe's expansion, could it simply be one possibility among countless others? Picture a cosmic lottery where every universe gets its own unique set of physical laws. Some might have no dark energy at all, collapsing instantly. Others could have so much that galaxies never form. Ours, it's the Goldilocks version, just enough to allow stars, planets, and life to exist. This idea ties into string theory's landscape of possible universes, where dark energy's value isn't special, it's just luck. Think of it like rolling a die with a trillion sides. Most outcomes lead to barren, lifeless universes, but a tiny fraction, by sheer chance, land on conditions like ours. It's a humbling thought. Our accelerating cosmos might not be inevitable, but a rare fluke in a sea of possibilities. Critics argue this smacks of giving up, saying, "That's just how it is," instead of seeking deeper explanations. But supporters counter that the multiverse could explain dark energy's puzzling fine-tuning without invoking a cosmic designer. After all, if every possible universe exists somewhere, it's no surprise we find ourselves in one that allows us to ask the question. The stakes are high. If true, dark energy becomes a fingerprint of our universe's place in a vaster reality, one where physics might be wildly different just beyond the edge of imagination. Up next, we'll wrestle with a pressing question. Should humanity invest billions in unraveling dark energy's secrets, or are there more urgent problems closer to home? The answer might surprise you. Now, let's shift our gaze from the vast cosmic mysteries to a more grounded, yet equally pressing question. What is the real cost of chasing dark energy? On one hand, unlocking its secrets could redefine our understanding of reality itself. On the other, billions are spent on space telescopes while hunger, climate change, and disease demand urgent attention. It's a moral tightrope walk between curiosity and compassion. Consider this: projects like the James Webb Space Telescope cost over $10 billion. That's enough to fund malaria eradication for years or build thousands of schools. Critics argue these funds could save lives today instead of probing an enigma that might never benefit humanity directly. But supporters counter that basic research has a history of unexpected payoffs. Think of how quantum mechanics, once purely theoretical, now powers your smartphone. Dark energy could unlock technologies we can't yet imagine. The debate gets thornier when you realize dark energy research isn't just about science, it's about survival in the very long term. If the universe's expansion holds clues to our ultimate fate, isn't that worth investigating? Imagine if civilizations before us had ignored similar questions. We might still think the Earth is flat. Yet, balancing this with present suffering requires nuance. Maybe the answer isn't choosing one over the other, but smarter allocation. Some propose a middle path using space research to tackle earthly problems. Satellite data already helps track deforestation and disaster relief. Could dark energy missions spin off similar innovations? Others insist humanity must multitask, feeding the hungry while reaching for the stars. After all, we're the only species that ponders dark energy and builds soup kitchens. As we wrap up this dilemma, remember, the choice isn't just about budgets but values. What kind of future do we want? One that retreats from the unknown, or one bold enough to explore it without leaving anyone behind? Next, we'll tie all these threads together as we stare into dark energy's grand finale and what it means for us all. As we bring this cosmic journey to a close, let's take a moment to reflect on the staggering reality of dark energy. This invisible force makes up nearly 70% of the universe's energy budget, yet it remains one of science's most profound mysteries. We've explored how it accelerates the expansion of the cosmos, debated its ethical implications, and even questioned whether we're prioritizing the right problems. But one thing is clear: dark energy challenges everything we think we know about reality. From Einstein's cosmological constant to cutting-edge space telescopes, humanity's quest to understand this enigma has pushed the boundaries of knowledge. Yet with every answer comes new questions. Could dark energy reshape physics as we know it? Might it hold the key to technologies beyond our wildest dreams? Or will it remain an elusive puzzle, reminding us of the universe's endless capacity to surprise? The story of dark energy isn't just about distant galaxies or abstract equations, it's about us. It's about curiosity, perseverance, and our unshakable drive to uncover the truth, no matter how hidden. So here's the challenge we leave you with: the universe's greatest secret awaits. What role will you play in uncovering it? Whether you're a scientist, a dreamer, or simply someone who gazes at the night sky in wonder, the next chapter of this mystery is yours to explore. If this journey through the cosmos sparked your curiosity, don't let it end here. Hit that subscribe button and ring the notification bell so you never miss our deep dives into the universe's biggest questions. Share your thoughts in the comments. Do you think dark energy will ever be fully understood? And as always, keep looking up. The stars have more stories to tell, and we're just getting started.